And I'm still so I think I didn't set the recording properly for the last session, so I have not. Yeah, it didn't appear there. So hopefully that'll work out. Here, I'm gonna, while we're still waiting for a couple more people, I'm gonna try writing a little bit more. Whoops, why is that not doing that? See, like I said, I know why. All right, there we go. It does some smoothing, and so some of the finer stuff I'm missing. Like it smoothed out that W. So it's not pretty, but it'll always be in focus, and it won't keep hopping off screen. Uh, Here, why don't you, while we're waiting for it, um, give me a happy or unhappy sign for how do you like this so far, the writing on the whiteboard. Happy or sad with your status? Camille surprised. Is that a so-so? Winky. Um, that's good, I guess. So winky smile. All right. Cool. All right. So Nick, 1, 2, 3, 4, 5, 6, 7, 8. Okay, cool. Yeah, before we get going, does anyone have any concerns or questions aside from the fact that yes, I am still behind with grades? That's a big one, and I hear it. I just have not been in a place to be able to do much about it yet. Okay, I'm going to take that silence as nothing. For right now, actually, I'm going to just go ahead and switch off my video because it doesn't convey anything except for the fact that I'm here. Hi. Um, I'm going to talk. Feel free to either chime in with a comment. You can do the raise your hand thing. It pings me. Any of those things. And yeah, we'll go ahead and dive in. So keep in mind, the upcoming assignments. I'm going to ask you to just kind of, sorry, as a way to, again, kind of gather together what we've been working on, to do a Chapter 7 summary for me for Friday now. We're just finishing up Chapter 7 right now, starting in on Chapter 8. So that's up on Blackboard, and I've adjusted the announcements sequence. Sorry, the schedule spreadsheet, and then for Monday, it will be the reading of section 9.2. We're gonna work on 9.1 on Friday, and then with a warm up and also the homework. So for the homework, again, I hope you've got a little bit of time to start in on it. It is a little bit long, but it's actually, there's a whole bunch of extra credit available on it. So like, you don't have to be perfect. If you don't get all the way through it, just submit what you've got, and you can still potentially get 100%, even though you've only done like about 70% of it. So the main thing is to get you looking at it and thinking about it is the intention there. Really quick question, actually. Has everyone seen the notes, the messages? No, never mind. Forget that. I'm going to back up on that. Sorry about that. Let's get started, actually. So what we're going to, we basically were a little bit short of time, not surprisingly, last time. talking about Maxwell's equations in matter, and I just wanted to kind of wrap that up, give it to us in a nice box, and then what we're going to do is we'll move on from there into the subject matter that's covered in Chapter 8. But let's start in with this. So again, I'm recording this. Let me know at any point if it's hard to read or anything like that. Yeah, we'll do the best we can. But feel free to interrupt with any issues, any questions. So Maxwell's equations in matter. So we had seen that including now the fact that we can have our polarization change means that we can now have polarization current, and then we regroup things and expressed some of our Maxwell's equations in terms of in terms of stuff that in terms of the displacement and magnetization. I'm sorry, and H. Yes, Camille, question. Yeah, the homework I posted yesterday. So you have a little bit less than a week. Again, if that turns out to be difficult to finish under the circumstances, let me know and I'll figure it out. I want to keep posting it regularly so that you don't fall behind unnecessarily, and we've got something to work on. But I will be flexible with you as much as needed. And just all I ask is that you have a little bit of patience with me. Cool. Submission will be on Blackboard too. All right, cool. Let's go back in talking about Maxwell's equation. So we've modified Gauss's law. Oh, can we have until Wednesday? Yeah, we can do that. We can do it till Wednesday. I'll go in and modify it. So what I'll say is, yeah, that's fine. That's fine. The next one will be for the following Monday, though, unless something comes up. Want to keep us generally tracking, staying basically on close to schedule, but allowing flexibility as needed. So, all right. Yay. Cool. All right, I'm going to keep going then. Going to be a little bit slow here, though. So we rewrote things in terms of our free charge and our polarization charge. And so we have our Gauss's laws before, even with our time-varying elements. We still have Gauss's law for the electric displacement appearing this way. And then we have still, as always, the fact that there aren't actually magnetic monopoles, so that divergence is always going to be zero. We're going to have, whoops, hitting the wrong buttons on my pen. Again, I'm asking you to be patient with me as I figure this out. Right, we got Faraday's law as well. And then again, looking at the Ampere-Maxwell equation right here, we gathered it up and expressed it in terms of our H, that auxiliary field, and the electric displacement. So this is worth putting a big box around. Oh, there's a box tool, but hey. So one of the things that's nice about these is they are succinct, right? They've got everything right there in these four equations with just a handful of terms. One of the things that's kind of annoying about them at the same time is that, look, they're mixing. We've got E's and D's, and we've got B's and H's. It would be nice if we had just our plane fields, or if we had just our auxiliary fields, like if we had just D's and H's, or if we had just E's and B's. Yeah, this is part of the price we pay. One of the things so here, I'll just say, yikes, succinct, but mixed, right? Nice thing is we can mix them. We can write it all in terms of E and B. In the situation where we're dealing with linear media. So yep, linear medium. So like that. So what do we mean by that? Linear media. So when D is this, not outside. Oh, if there's no medium at all present, then our D and H will be equal to E and B. So vacuum is a linear medium with epsilon here being equal to epsilon naught, and likewise mu being equal to mu naught. So right. So the one time when we have to deal with these mixed Maxwell's equations, if we're inside of a nonlinear medium. But yeah, vacuum we can count as a linear medium with epsilon equals epsilon naught and mu equals mu naught. Cool. So here they are in differential form. What I should be doing, I'm going to get fancy here. Give me 1 second. Let's do the same thing in integral form. Right. So start off with the integral form of Gauss's law. So the, whoops, pardon me. That's supposed to be a D. Right. So the flux through a closed surface of D is going to be given by the free charge that's enclosed. Same thing, the flux, that's a little bit better, of B through our closed surface. It's always going to be 0 since there are no monopole sources. We can do a path integral. Oops, that's not as pretty an integral. So again, notice this is through a surface, that's through a surface, this is through a little path, right? And so this is Faraday's law, so we can do right. And so that's going to be given by the negative time rate of change of the magnetic flux there. Right. And so we can write something similar for our Maxwell ampere law, and I got to give myself enough room for this. So that's not a bound. That's just telling us that we're going around a closed loop in a path, though, right? This is a one-dimensional integral. Yes, that's P for path, indeed, right? So if I point right here, right, we're integrating E dotted with DL. So we're following the path around instead of taking flux through a surface. So how much the vector field goes through the surface area. Here, cool, awesome, thank you. And they keep giving me feedback because in class I can see your facial expressions. And the integral of b. So I'm sorry, I'm going to pop back to that question. Over the surface area, yeah. So the unnamed Maxwell's equation right here, this has got to be over a closed surface. And so one of the things noticed right here, whenever we do the circle on the integral, that means it's a closed surface. This is a closed surface. Here, this is a closed path. Here, this is the surface formed by the path. And so if we've got a path that's like a loop, then this surface here is not going to be closed. It'll just be like a membrane across the closed loop that's over here. Cool. Awesome. Be weird if it was enclosed by the loo. Yeah. All right. So let's do the same thing over here for our Ampere Maxwell law. Right. So where's this? I should have left more space. I apologize. So where is this integral around a path coming from? No, it's what we're doing is doing an integral over the area over here of the curl, but then applying Stokes' law, and so then it becomes an integral around this closed path that enclosed the surface area. All right, so continuing. Right, so this is given by whatever free current is enclosed, and then we have this additional term right here that is coming from the rate of change. This is Maxwell's addition. So this is the rate of change of the displacement field. Another way, just right, and then that's coming from the displacement current in vacuum. So we can write this: the rate of change with time of that displacement field dotted through that surface area. Cool. So again, we've got this integral form, and we can put a dotted box around it. These are also going to be really, really useful to us, but of course they can just be derived from the differential form over on the left. So in the textbook, it has some more stuff about boundary conditions and rule fields at a surface when you go from one medium to another, stuff like that. We're going to pass over that for right now, but it's actually quite important because we're going to use that specifically when we come back to looking at waves when they hit the interface between two different media. And that's going to be the key to a lot of optics. Okay, cool. So we've got this summary here. Part of the next homework assignment deals with these things right here. Like I said, we're going to basically just put a pin in these and hold them right here and come back to them once we've done a little bit more with waves. But before we do, questions? Cool. Trying to give a nice long pause. If you've got something but it's going to take too long to type or to speak, you can also just raise your hand with that button there. All right. Cool. Well, not hearing anyone screaming. Let's actually draw a big line in your notebooks, and we're going to move on to now starting to take a look at the consequences of Maxwell's equations now. And and just in general, taking a look at time-varying fields. So now we have Maxwell's equations allows us to take on electrodynamics. So we're not just doing electrostatics or hydrostatics. Electrodynamics is electricity and magnetism with changing fields. And so if we look at changing fields, one of the things whenever we have stuff that changes, obviously that's a lot more interesting than stuff that's static, but it can also be a lot more complicated, and that's why we don't start there. So one of the ways we deal with changing things, and this is a theme that we started all the way back in Fun 1. One of the ways that we can look at situations where things change and you can have rather complicated stuff going on is we can take a look at conservation laws. And so that's the motivation for Chapter 8 is taking a look at quantities that we saw that were conserved. So I'm going to erase this, and here, let's start a new thing, right? So all right, I'm not sure that typing leaves me being silent for a while, but yeah, there we go. Conserve. So perhaps like the first thing that you learn about when you learn about conserved quantities in Fun 1 is, as an example, is mass, right? Mass doesn't just appear or disappear. Ooh, okay, until you get to Fun 2 and learn about relativity and E equals mc squared, but under kind of normal conditions, or what we can do is we can extend it and talk about mass energy, but under kind of normal relativistic circumstances, mass is a conserved quantity. So we've got something similar for that right here, and then that's conservation of charge, right? So we know that we've seen this before, that anytime there is charge decreasing in an area, it means it had to have flowed out of that area. So we can do a couple things. Yeah, we on Chapter 8? Yeah, we are on Chapter 8 now. Conserve quantities, right? So we're looking at charge first. Oh, okay. And I'm going to switch over, right? And so we wrote this. There are a couple different ways to talk about this, right? We know that we can write it in integral form, that in a certain area, certain volume, any change in charge has to be caused by current flowing out of the area. And we put a minus sign there because current going out leads to a decrease in the charge, right? And by convention, we have outwards is the positive direction for our dA variable on the right. So the differential form of this, though, is just to say that instead of talking about Q, we can talk about the charge density in an area, and instead of, we can use the divergence theorem and convert the integral of the current flux through the closed surface into an integral of the divergence of J, and then we're just stopping the integral part, the integral over volume, and so this becomes negative divergence of J, right? So this right here is kind of, right, so this is sometimes called the continuity equation. Give me a second. Let me see if, does this work? No. Forget it. That's not a very efficient way to do this. Right, continuity equation for charge. There we go. All right, so we can, and the book talks about how you can take this and take that as a fundamental thing, like a fundamental assumption right here. Or the other thing we can do, though, is we can start from Maxwell's equations and not assume continuity. And from Maxwell's equations, you can derive continuity, right? So, you know, you say, well, what's the difference there? Well, in our derivations of Maxwell's equations, we started with the assumption of continuity, but we can also flip things around and start with Maxwell's equations and derive continuity from them. All right. Cool. So after mass conservation, right, as kind of an example, oftentimes the next conserved quantity that people learn about in like Fun 1 is energy, right? So here, let's just box around this off to the side. Cool. And now we're going to do, let's take a look at energy as our next conserved quantity. So actually, looking ahead, besides energy, what other conserved quantities did you learn about in Fun 1? Go ahead, type them in the comments. Momentum, okay. And what kind of momentum? Linear? Sure. So linear momentum and angular, and angular, and angular. Cool. Yeah, so there we go. We're going to have the exact same thing, right? They don't stop being conserved. So what we have to do, though, is first take a look at the expressions that give us these things. And so we're going to, yeah, let's take a look at it at energy. So, so let's start off with the expressions from electro and magnetostatics right here. That was just me stalling while I change this over. Cool. So we've got, and again, so we can't really use the E for energy because we're using it for electric field, and but we can talk about electrostatic energy right here was epsilon naught over 2. And we integrated inside a volume, the energy is proportional to the electric field squared. And we're going to come back to that E squared aspect of it later on. And for magnetostatics, I should have left more space. So we can already guess what this is going to be just from analogy, right? Everywhere we had an epsilon naught, we've got a 1 over mu naught. So the 2 stays in the bottom, but the denominator there, but we've got a mu naught. Everywhere there's an electric field, we have a magnetic field, right? So sure, that's fine for electrostatics and magnetostatics. One of the things we can do, though, is take a look at, well, what's going on here in electrodynamics. Okay. So now we've got charge and current and fields, electric fields, magnetic fields, and all these things are changing in time. So when I say current, it's really going to be current density. So we're going to look at, hey, well, how much work is done to move our charges around, so our rows moving around as currents in a little bit of time. All right. So, all right, we're going to do a bunch of math. Again, this is a good way to take a look at all of our vector calculus and pull together a bunch of the stuff that we've been looking at before. So, all right, we've got some little bit of work, so a little bit of time. We're going to, in DT, we're going to do a little bit of work, DW. Oops. So, all right, the work is going to be given by the force on our charges, right, dotted with their displacement in that amount of time. And so, all right, well, we know what the force is from these fields, right? So as QE is the electric force and QV cross B is our magnetic force, and all of that, again, dotted with DL right there, except I'm going to do one thing with that DL right there, and I'm going to change that. So let me see if I can. So instead of...
Is that the curl of B?
It's no. So that's V cross B. Here, let me come back to that in a second. Cool. So we're going to fix this bit right here. So yeah, this is, so our force from on a charge Q from an electric field is just QE, right? That's the electric force. And what is the force on the same charge in a magnetic field? Well, if it's just sitting there, there's nothing. But if it's moving, then we get a force Q V cross B right there. Cool. And so now instead of dl, right, we know the charge is moving with some speed v, so my dl, and actually it's a velocity v, so v dt, right? So yeah, let's do this. Why is there Derek number 2? Because he's really good at cloning himself. No, because he was logged in and then he left. Right, so this part here was our force, and this part right here is the DL. So we look at this, and one of the things, though, that we can see is we can actually simplify this, because right here we've got a term that's V cross B dotted with V. And we know something when we've got this term V cross B. What's the dot product with V going to be? You tell me. What's the dot product of V cross B with V? And you're like, I don't know what B is. I don't know what V is. These don't even have to be velocities and magnetic fields. I could call this A cross B. I could call this A cross, yeah, all right. It's going to be 0. Why? Because the cross product is always perpendicular to either of the elements. So V cross B is perpendicular to V. Dot product with V gives you 0, right? So I'm just going to simplify out right here, and we get Q E right here dotted with V, and then the dt term. Cool. All right, and then next step, let's make life a little bit not simpler, actually a little less pleasant. Oops. Can I go backward?
Sorry, V cross B what to V?
Is perpendicular. Does that make sense?
Ah.
Right. So that's why that's why that term just went away. The dot product was 0. Cool. Yeah, keep asking me these questions.
Gotcha, thank you.
Cool. Because if I don't get questions, and we're talking like that, and I'm talking, I don't know if you're following me. So our Q right here, I'm not going to say equal, I'm going to say let's replace it with a rho d tau, right? So really what it should have been was a dq, right? So now, right, or actually, I'm sorry, let's do it this way. dq is equal to rho d tau, so q equals the integral of rho d tau. That's another way to do it. So our little bit of work right here, we can write this as an integral. Again, this is over some volume. We've got rho d tau, and then the E dot V term. And the reason why this was still an infinitesimal amount of work, dW, is it's happening in a little bit of time, dt. But this is integrating over, this is the total work done in this volume, and so that's why we integrate over the volume. Okay, and then, oh, here, let's notice one other thing right here. We're going to start mathing this, basically. We started out with a little bit of physics up at the top, and now what's coming out is just working through the math. Rho v, those right there. We can put those together. Right, so we've got moving charge density, that's a current density, right? So I'm going to group those together, and then the other thing I'm going to do is I'm going to move, here, let's do this. I'm going to move this dt over to there. So now if we do that, we can start to rewrite all this stuff, and we can talk about a dw dt, like that. Sorry, when I moved it over, this isn't necessarily clear. What was moving was the dt. All right, and so this is going to be given by the integral, again, over this little volume. We're going to integrate over the volume, so we'll move the d tau later on. And so we've collected the rho and v into a j, and so we've got, yes, I just divided that out. And yeah, we're treating it, it's a differential. It can be, in this case it can be, because it can come out of the integral. We can take the dt out of the integral, because notice this is an integral with respect to space. So dt in this case is a constant with respect to the integral, right? If dt somehow depended on our spatial coordinates, then we couldn't just do that. But because this is just a spatial integral and space is completely independent of time here, we're cool doing it. All right, good. Yeah, and so that's one of these like hidden things. Your calculus teacher tells you, oh, don't treat your differentials like little like separate variables. In physics, sometimes we can do it. Is that, yeah, dt is a constant here. It's a constant with respect to our integral, because it's just a spatial integral. it's not going to be right. It's a little infinitesimal bit of time. Other times later on, we may want to do a time integral, in which case we can't just pull it out, right? dt is part of our integral, but in this case, it's a constant with respect to the spatial integral. Cool. So here, this isn't work. This is the work per unit time. All right. So we're cool. We've got it. All right. So yes, power, right? So we ask for, well, what's the work done, right? This is work per time, right? And that's power. Cool. If that's just what we wanted, right? We said, hey, what's the work being done, right? Why did I put some dot, dot, dots? Well, it's kind of a pain, right? You got to know the fields. You got to know J. When we started out for electrostatics and magnetostatics, we wrote everything in terms of our fields. It'd be kind of nice to do that. So the next little bit that we're going to do right here through the end of the class is we're going to rewrite this in terms of our fields. Cool. So that's our task for the last part of the class right here, and it involves just doing a bunch of vector calculus because we've got our J, so we can take J out from Maxwell's equations, stuff like that. So that's our first step. Oh, I'm sorry, changed my pen. Oh no, don't do that. Right, we're going to use the Ampere-Maxwell law to eliminate J. Really quick question. Can you see as I type, or is it only, does it all appear all at once?
All at once.
All at once. Okay. Yeah. Okay. I'm sorry about that. Okay. So I'm going to try to work with that. So, all right, let's take our Ampere-Maxwell law. All right, so we've got, again, just a refresher. And these are one of these things, if we had quizzes, what I would have been asking you to do next was to memorize Maxwell's equations, 4 of them, not a whole bunch. We're not going to do that. What we'll do is I will give you just really simple problems, and you'll have them in front of you, but you have to know, I'm probably going to use words, and so you'll have to understand how to relate the words and symbols. And it'll be time, but it'll all be on Blackboard, and we'll figure out a way to make it work. I'm hoping that by making it open book, right, it makes you think about it, but low stakes and actually open book, hopefully easier to score well. All right, so we're doing this in vacuum for now. We'll go back and tweak it inside of materials, but yeah, this works out okay. So next step we want to do is we want to get that J by itself, right, to get rid of it. So we can write this as there we go, right? Got it by itself, so now we can substitute it in. So here, let's not write out the whole thing. Let's just take a look at this E dot J term now. Becomes, all right, well, we got a 1 over mu naught hanging around. So E dot curl of B, and here we'll put this term in parentheses carefully. And then we have the epsilon naught term, the second term. We substitute that in. We've got an E dot dE dt. Right, and so one of the things when we look at this, we can notice what we ultimately ought to get something that reduces back to what we had for electrostatics and magnetostatics. And remember, this E dot J term is coming from inside of this dW dt, right? This power term right here. And E dot dE dt, well, hey, if you integrate that eventually with respect to time, because this is just, the rate of change of energy with time, if you integrate this with respect to time, we should get an E squared term, which would be nice. So one of the annoying things, though, is this term right here, right? That's going to be kind of a mess. And so this right here, we've got an E times a derivative of B. That looks like 1/2 of a product rule, right? Or another way to say this, which is if we eventually wanted to integrate that, that looks like a case for integration by parts. But again, integration by parts is really just the product rule rearranged. So hey, you wouldn't know what the product tool is because that's not a thing. Product rule. So here, let me write that in like a different color. Product rule. All right, so what we're going to, so the E dot curl of B, that is what we're going to be actually doing is saying that, oh, I'm sorry, wrong. That's actually going to be coming about from a divergence of E cross B. That's going to be one of the two terms. All right, and so this is going to be given by okay, so that's what we're going to be using right here. Before we do that, though, oh, so notice, why is there a minus sign? Well, vector calculus, we can see that if we had distributed things, we might have gotten different orders and stuff like that. And so when we switch the orders around, we end up with this minus sign. You can track it through with the vector calculus. So before we proceed with it here, we know what these things are right here. We've got this one from Faraday. We've got the first term from Faraday's law. We can do that. So let's write this right here. So the curl of E we know is minus dB dt. Oh, look, we've got a B dot dB dt. So that's also going to probably be helpful in terms of giving us our B squared term. And then over here, we still have the same term. Cool. All right, so we're going to take this oh, why did we leave that term? Because we're going to rearrange this and sub for this term right there. So here, actually, let's. Right. We're going to sub that back in. So let's keep going with our E.J calculation. Right, so we've got from above 1 over mu naught E. So now E dot curl of B right there, we can write that whole thing as first this term minus B dot dB dt. Right, that's the term right here. That's the term just before the orange circle, and then the term on the left-hand side of the purple equation. All right, and all that was the first term in E dot J, and then we've got the second one right here, and we're going to leave that one unchanged. Yeah, Harry.
It seems like the negatives in that term by the 1 over mu naught seem off from the equation before. Shouldn't it be? Oh, never mind. I couldn't distribute things properly.
No, it's all good. Yeah. So take the orange circle term, move it over to the left so that it's positive, and we're going to substitute in the positive thing, and then take the term from in the purple equation, move it over to the right. It picks up a minus sign, and then the term that didn't switch sides, it already had a minus sign in it. So yeah.
Yep. Okay. Yep. Thank you.
Cool. No. Good. And so. Yeah, and so here's the thing I alluded to before, right? Let's get this right here. This, pen, sorry. This term right here, that right there, this is 1/2 of, that's a half, 1/2 of the temporal derivative of b squared. And then this term right here, again, that's 1/2 of the time derivative. Sorry, my derivatives look like 2s with this pen. Okay. So what we're going to do with this right here, here, I'll give you a second to take a look at this. Yeah, Nate.
Is that a partial, or is that a, like on the first part, like the 1/2 ddt? Is that a partial on top, or is that a?
Yeah, it's going to be a partial, and so my there we go. It's supposed to be a partial.
So that's supposed to be a partial and okay, a partial on the bottom. Okay, I just wasn't sure.
Yeah, well, because in this case, because time, b is varying with time and space, so we're just taking the time derivative. So yeah, we got to opt for a partial here.
Okay.
Yeah, sorry about getting that messed up. Cool. So what I'm going to do right here, and leave myself enough space, is collect these terms, and then, yeah, Harry.
How do you get the 1/2 coefficient when you combine the b dot?
So
time derivative.
Yeah. So what would be the derivative if we just did the time derivative of b squared? We would get 2b db dt, but we don't have the 2 out there, so we got to have we're canceling out that factor 2 that should be there with the 1/2.
Oh, I see. Okay.
Yep. No, but good. So here, let's just collect all that stuff together though, because we've got now two of those time derivatives right there. So I'm just gonna write this like this. So minus sign actually was present on both of those. I just didn't carry it down into the orange. So minus 1/2. Oh, I'm sorry. I'm sorry. Let's put the DDT out here. And that's supposed to be partial. Sorry. That's a DDT, which is not looking very pretty. Give me 1 second to fix this. That's supposed to be a squared. Sorry. Oh, I am sorry about that. So minus 1/2 ddt of the quantity 1/mu0 b squared plus epsilon naught e squared, and then minus then the other term that we haven't done anything with, which is the middle term in the blue equation above it. Okay, cool. All right, so we've gathered all this stuff together in the E dot J, and remember what we're eventually going for right here is the dw dt, the power, is the integral of E dot J. So we okay with this right here for a second? I'll let you take any additional notes, and I'm just as a backup going to do something here. Cool. All right. Thank you. So I'm going to erase this and move on. We're going to take that expression, and we're going to now we have to integrate it with respect to volume right here. So, whoa. All right, there it all goes. So again, we were looking for this right here. No, I know. I kind of feel like it took forever to write that all out. Right. Yeah, it's true. Right. Instead of like talking about how quickly that goes, we could say, well, in comparison. Carter's asking about E cross B, and that, yeah, that's going to be really, really important. If we're talking about, if you remember, we caught a glance of this maybe in Fun 2, also in high school, that electromagnetic waves, we say, hey, the fields are perpendicular. And I'm going to say, yes, but the electromagnetic waves in vacuum, the fields are perpendicular. In confined spaces, and we're going to learn about this at the end of chapter 9, they no longer have to be perpendicular. And so, yeah, things will get interesting. But to begin with, yeah, and that actually, we may run out of time, but that is going to be one of the things that determines like the flow of energy, is exactly that. Is that E cross B will point in the direction that our energy is going to be flowing, and hopefully we'll get to that. So what I've done right here is from the previous expression, remember we had the first term had the time derivative of the b squared and the e squared. So I'm pulling that time derivative outside my integral. And this is an integral, again, just to make it clear, this is the spatial integral. That's why it's okay to pull the time derivative out. and then we had the 1/2. Here, I'll switch the order, put the e's first. Otherwise, it's just the exact same expression. And again, we're integrating that over space. And yeah, Harry.
Is that a partial derivative out front or a normal one?
In this case, it's now a normal one because we're collecting, this is because we've integrated out the spatial components, right? So B did vary with space and time, but once we integrate over all of space right here, we no longer have to worry about that. So it could be a partial one, but actually an ordinary derivative, it works in this case because we've integrated out all the spatial variation.
Okay.
And so, yeah, if I were a mathematician, I would make a much bigger deal about that. But as a physicist, I follow the rules of math, but I sometimes kind of don't make a big deal about them and minimize their importance. So we were following the rules, but I didn't actually explicitly point out why. So the other term, right? So this is the ddt only applies to that first integral, right? We only had the derivative term for part of it, and then we had this, we had the e cross b term with the divergence, and so we integrate that also. That was still within the integral, but we're going to write it as a separate one, so we don't have to worry about the ddt part. And that was 1/mu0 divergence of E cross B. Integrating all that up right there. And so we'll look at that, and hey, we're integrating a spatial integral of a divergence, right? And so spatial integral of a divergence. So we know what to do in that situation right there, right? What do we do? Divergence theorem, right? So I'm going to write that term first. Well, here, let's just do d. Oh, gosh, sorry. I can't write quickly because then it thinks I'm writing big. So we're going to turn this, use the divergence theorem, this into an integral over the surface of that, of what's in the contents of that divergence. Right, and same thing over, same expression as before over here. Yeah.
Is it still a d tau when we're integrating over that surface?
No, it is not. Thank you. Cool. That should be a dotted with a dA. Right. The integral of the divergence, which is the derivative over the region, the volume, should be equal to the integral of the actual function over the boundary, in which case is the surface. I have to do a dot dA. Thank you. Cool. So, and then this one, I'm just going to rewrite this, hopefully not too sloppy. Right. And so what we've got now, right, this is the power in a region, and we can write it two ways, right? We can break this up into these two terms right here. So this bit right here, the inside, the integral right here. This is the energy, right, of the electromagnetic fields. And let's call that big U, electromagnetic. Right? And so what we've got then is, sorry, we've got three terms. So remember, this was the work done per unit time now, right? The rate of work being done on the charges. So we can call this a theorem right here. So if we were to integrate it with respect to time, we would get the work done on the charges. And that's going to be equal to, the first term is the change in the energy of the fields, right? ddt of the energy of the fields, but then we integrate it with respect to time. And then we have the second term minus something right there, right? And so there's got to be, so the first thing is, all right, we've done some work on the charges, and that work was done by changing the energy in the fields, but we can also have energy that just leaves that flows out of the region. So energy can go into the changing moving around the charges. Or it can flow out of the region, and that's the only way we can change the energy in the E&M field. So minus okay. All right, and so that gives us actually a moment to take a look at this last term right there. Wow. Okay. So yeah, I'm working on getting my times right. So we're gonna give this a name, and then what we're gonna do in our next class is figure out is actually practice this stuff a little bit. Give me 1 second. So no one caught me on this. This is still a cross product up here. And so I'm going to take this bit right here. Whoops, really this part right here. That bit there. And we're going to give it a name. So this is the energy per unit time per unit volume that's carried by the fields. So let's give that a name. Oh, it ran off the, dang it. Carried by the fields. In both fields. And so what's the name of that thing is called the Poynting vector. All right. So here, let's just define that. And we give it its own, name. So I'm using the 3 because I'm defining the symbol right here. So that's supposed to be, is defined to be 1 over mu naught E cross B. Right there. So it's the energy per unit time per unit volume. Pardon my spelling. Another way to say this is, so energy per unit time is it's the rate of energy density, though, right? Because energy per volume. So it's the rate of energy density flow is one thing we can say about this thing. And another thing we can say is it points in the direction of the flow. right? So let's finish up with just interpreting this thing right here, right? So the same way we had before, the rate of change of charge was basically given by the change of any charge before, and then minus any charge that flowed out of an area. Now we've got the rate of change, the work done on the charge is given by the change in the energy of the fields minus any energy that the fields carry out of the region, right? So we'll keep working with this some more. Yeah, I'm out of time. I don't want to keep you later. I'm still working on figuring out how long it's going to take me to do these lectures, and the answer is slower than normal, more time to cover the same material. Let's wrap up. How are we feeling about this? Yeah, Camille.
Where can we rewatch this lecture?
Yeah, so I am very much hoping that it will be you can go to the virtual classroom to the and there should be you should be able to select recordings. I will post instructions on it. The first thing I want to do though is see if it actually worked, because I tried to record for the first one and no, it didn't work. So it somehow didn't save it. So I am working on that, but I'll let you know. Cool. Actually, can I really quickly poll you? Derek is surprised. Actually, I'm going to do a poll right now. Polling, multiple choice. Basically, the question is, which do you prefer? Yeah, right, the discussion. So pen and paper, this whiteboard, or we'll just do either. Here, go ahead, give me a quick, let's see if, did that go? You are polling. All right, it's polling. One person hasn't responded. Oh, probably me. Hi, how you doing? I haven't responded. Okay, so we have, yeah, exactly. Ha 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 ha. All right, we've got three people, either two people whiteboard, one person pen and paper. All right, I will see. Basically, I think the determining factor for me will be whether this recorded okay and how easy it is to watch recording. What do I like? I think in some ways I like the pen and paper better, because what I can then do is scan it and post it as just a PDF for you, which, by the way, I did from the last class. I forgot to add that. I scanned in the notes, and they are in now a new section called Notes. But what you don't get then is the accompanying lecture. So what I could do is I can try also recording that too. Anyways, I may give this one more go, but then we'll and make a decision after that. But I appreciate your patience, everyone. I also appreciate the fact that, wow, I ran over a little bit. Did not mean to do that. But anyways, for next class, we have done everything in chapter 7, so you can look back over it, write up a summary, and start in on looking at the homework, because more than half of it you now can do. And the other stuff, if you looked ahead at the reading for chapter 8, you could also do some of that too. Yeah, I guess so. If you got a class right after, you just click over in your browser or whatnot. All right, cool. Thanks, everyone. And if you have questions between now and class, the next meeting, feel free to email me. But otherwise, yeah, be well. Take care. All right, see y'all.